Alright, this video is going to consider something that is very near and dear to analytical chemist's heart. That is ways to quantitatively describe the amount of material present in a sample, concentration units of measure, essentially. This is a very important topic for analytical chemistry class. You need to know these units and know how to convert between them. That's more or less simply stated what you need to know how to do. You will see problems like this on more or less every exam that involve these base units, so it's important that you understand what they are. Also on standardized final exams, it's popular to give you questions where you need to convert between units of measure for concentration, so you need to know their definitions and how to convert between them. Very important. Now, if we're going to describe a few different units of measure that we can use, which we're going to do through the remainder of this video, we may choose to use mass percent, mass volume percent, parts per million, parts per billion, parts per trillion, mole fraction, mole percent, or molarity or molality with the L. So let's review these. You may have seen them before from, say, a general chemistry type of class or an introductory chemistry type of class. But it is very important that you familiarize yourself with the definitions if you are confused, okay? So the first one is mass percent. It's a very, very simple way to express the concentration of a solution. Typically, if you're going to express results in mass percent, you would have some number, percent perhaps, and then you would write m/m like I've got in the brackets here. That's to tell everyone that you're talking about a mass percent, not a volume percent, okay? So don't forget to include that, and if you see that, that's what that means. It's a mass percent. Very, very common. It's a measure of the mass of a solute. It's the minor component. Oftentimes it's a solid. It doesn't have to be just a minor component of a mixture, per the mass of a solution, expressed as a percent. So if I'm going to write that out, which I like to do sometimes in a mathematical statement, I would have the mass of the solute divided by total mass of solution, and then I got to express it as a percent, which means I need to multiply it by 100. So in this particular example, let's just say that we've got about 5 grams of salt. I don't know if you can read that, but it reads 5.00 grams. It's like it's on a balance of sodium chloride salt. Let's mix that with exactly 95 grams of water to make 100 grams of solution. Okay, what's the mass percent of sodium chloride? Well, this is a pretty easy problem. My mass of my solute is 5 grams. The total mass of solution is 100 grams. Grams unit cancel, I multiply by 100. It's 5% by mass. Alright, simple enough. Mass percent. Easy concentration unit of measure. We use mass percent a lot if we're dealing with pretty concentrated solutions. The next one to consider is volume percent. Volume percent also has an abbreviation, just like the mass percent had. But for volume percent, we use V/V. Okay, V/V. We use this a lot when we're talking about liquids because it's just experimentally perhaps easier to measure the volume of liquids in the lab rather than the mass. So there's no reason why we can't use volume percent to discuss the concentration of liquids, which are miscible with one another. Example of where this might come up like is in liquid chromatography. If you're mixing solvents together to make a blend for your mobile phase, you might say it's 80-20, solvent 1 compared to solvent 2, and that's usually a volume percent, okay? So the volume percent is a measure of the volume of a solute per volume of the total solution, expressed as a percent. So again, if I'm going to write that out in mathematical terms, on the bottom here, the volume of the solute divided by the volume of the solution times 100 to express it as a percent, that equals my percent V over V, my volume percent. Simple enough, okay? Now these volumes should of course be the same units of measure, just like in the previous case with the masses, should also have the same units of measure. You can do grams and grams in the case of mass, kilograms and kilograms in the case of mass, milliliters, milliliters, liters, liters. It doesn't matter as long as they're the same. They got to cancel out basically, okay? So let's consider this example just really fast. Let's say you mix 10 milliliters of ethanol. It's drinking alcohol, of course, with 90 mils of water. And when that happens, let's just say for the purposes of our discussion that you get exactly 100 milliliters. Turns out, in reality, you might not get exactly 100 milliliters. There's no guarantee if you mix volumes that you get exactly the sum of their results. Okay, so do know that. But for this example, I'm just basically saying that that happens. Okay, it may not in real life, but just for this example, we're going to say it happens. So let's compute the volume percent of the ethanol in that mixture. Now you might be confused, okay, like which one's the solvent, which one's the solute here. The solvent is always present in larger quantity or else determines the phase. So that's our water here, and our solute, of course, is the ethanol. So my volume of the solute looks like was 10 milliliters ethanol. I am going to divide that by the total volume of the solution, which was 100. Multiply by 100 to express it as a percent. And sure enough, you get 10%. Of ethanol. Alright, so that's volume percent. Moving on. Another very, very important unit of concentration to think about is parts per notation, okay? Turns out there's going to be 3 separate units of measure that we can use in parts per notation. They are parts per million, parts per billion, parts per trillion. They sound like they're different, but they're actually defined in a very similar way. There's just about a factor of 1,000 difference between each of these units, as we'll soon see, okay? But the way they're derived is very, very similar, so it will make a lot of sense hopefully to you here in a couple minutes, all right? If we're going to use this parts per notation business, the concentration of the solute probably going to be a lot lower than it is in the case of like mass percent or volume percent. If you're doing mass percent or volume percent, you probably have a pretty high concentration of solute. If you're using parts per notation, that concentration is way lower, okay? Now, the thing is that it's pretty easy to understand, because all we're doing here is we're going to express our concentration of our solute as a part or a fraction of a larger whole. And if we're using parts per million, we're going to express as a fraction of a million. If we're using parts per billion, we're going to use expression as a fraction of a billion. And if we're doing parts per trillion, now you see we're going to do it as parts per trillion, okay? The only question then becomes, well, what basis for measurement are we going to assign these parts, okay? And it turns out most often that's going to be done on a mass basis, okay? On a mass basis. So, if I had 1 gram of solute in 10 to the 6, which is 1 million grams of the mixture, wouldn't it make sense to call that 1 part per million by mass? Of course it makes sense, right? And it turns out that that's exactly how this is defined. Okay, we typically define on a mass basis. You don't have to if you're dealing with gases, say, dispersed in the atmosphere. You might see this defined on a volume basis, and then oftentimes it's like ppmv or ppbv. The V stands for volume, and that's just based on a volume mixing ratio. So you could do like liters of volume of the different gases. Okay, the liter of the gas in question to 10 to the 6 or 1 million liters of air, say. Okay, but oftentimes in the chemistry lab, other than the gas analysis, we're talking about on a mass basis. Is kind of our fundamental basis for definition. So 1 gram of solute in 1 million grams of mixtures, part per million. Okay. Similarly, what if I did 1 gram of solute in 10 to the 9th, or 1 billion grams of the mixture? Wouldn't that be 1 ppb? Sure. All right, and that's all we're doing here. That's all we're doing, okay? So it might seem confusing at first, but it really need not be. Now, in addition to just defining things on this pretty simple mass basis, okay, for this parts per notation, we can extend our discussion specifically to the case of aqueous solutions. Now what I'm going to describe after is really only for aqueous solutions. It's important to understand that, okay? Aqueous solutions, of course, are water-based solutions, very common in the chemistry lab. And since they're so common, we'd like to extend our discussion to just considering water-based solutions in which a small amount of solute is dissolved within that water solvent. Now, where are we going with this, okay? Well, we learned in introductory chemistry that the density of water was equal to what? Right about 1 gram per milliliter. The density of water is right about 1 gram per milliliter. So if we have a water solution that is pretty dilute, in other words, there's not very much solute in there to change the density, the density of that resultant solution is right about 1. Now, why is that significant here? Well, couldn't I then, instead of writing 1 gram of solute for 10 to the 6 grams of mixture, if I'm considering an aqueous solution, couldn't I write 1 gram of solute per 10 to the 6th milliliters of the mixture? Isn't that in fact equivalent? Because the density is 1 gram per milliliter, so 1 gram, 1 milliliter, convert grams to milliliters, and I can write this. 1 gram of solute to 10 to the 6th grams, or 10 to the 6 milliliters of the mixture, excuse me. And if I took this expression then and reduced it down some, because 1 million milliliters, that's kind of a lot. We usually don't use the volumes that large, so let's divide both the numerator and the denominator by a factor of 1,000, or 10 to the 3. So if I reduce both, then I would have 1,000 milliliters in my denominator, which is equivalent to a liter, and a milligram of solute in my numerator. I just divided both of those by 1,000. Okay, so then this becomes equivalent to 1 part per million. So it's oftentimes said that for dilute aqueous solutions, it has to be a dilute aqueous solution, the density has to be close to 1, okay, for this to work. That a 1 part per million solution of a solute is equivalent to 1 milligram per liter of that solute in terms of its concentration. We use this a lot in analytical chemistry, this approximation for the dilute aqueous solutions, okay? Now, with regards to this parts per notation, if you see a problem on a semester exam or an end of semester exam, you need to be really, really careful what that problem's asking you. Okay, it usually asks you, what's the concentration of calcium in parts per million, or what's the concentration of this in parts per million? Read the question carefully, okay? And the trick here is not really a trick, but you need to report the answer that the question's asking for, okay? This comes up a lot with, like, if you're dealing with ionic compounds, like calcium sulfate or silver nitrate or just whatever it is, okay? You may think that you need to include the nitrate or the sulfate in the calculation that you have to do, but if they're asking you for the parts per million of silver or the parts per million of calcium, you don't. So you need to report what they're asking you, I guess is what I'm trying to communicate here. And if they want parts per million of silver, you need to tell them how many milligrams of silver per liter you got, or how many milligrams of calcium per liter you got in the case of calcium. All right, so please keep note of that, or keep that in mind as you work problems throughout this semester, okay? So that's parts per million. 1 milligram per liter is parts per million. Now, what about parts per billion, parts per trillion? The story here is very, very, very similar, okay? The only difference is a parts per million, a billion is smaller, right? Didn't we say that was 1 gram per 10 to the 9th grams of the mixture? So 1 gram of solute per a billion grams of the mixture. And then part per trillion, well, that's 1 gram of the solute per 10 to the 12th of the mixture per trillion grams mixture. Okay, so these are actually smaller units of concentration, by 1,000-fold relative to parts per million, and by 1,000,000-fold relative to parts per million. However, other than that, things can work very, very similarly. If we're considering the dilute aqueous solutions, 1 part per billion is equal to 1 microgram solute per liter of solution. And again, this is only if we're dealing with dilute aqueous solutions, okay? And then lastly, in the parts per trillion case, okay, since this is 1,000 times smaller than this one, we can write that 1 ppt is equal to 1 nanogram of solute in 1 liter of solution. And again, these simplifications only work for dilute aqueous solutions, okay? So a part per trillion concentration is exceedingly small. I've heard it reasoned that 1 part per trillion is like 1 drop of water in an entire Olympic-sized swimming pool, okay? So very, very low concentrations here. Not many analytical methods can measure in this parts per trillion range, as it turns out. Okay? But that's what we mean by parts per notation. Okay? Moving on then. We've got molarity. This one's everyone's favorite. Okay? Capital M is the abbreviation for molarity. We tend to say molar behind the number, so it might be a 2 molar solution or a 0.1 molar solution. Most common unit of concentration, you've probably seen this before. In molarity, of course, capital M is the moles of the solute divided by the liters of solution, the total solution. Okay, that's our molarity. A very closely related term is molality. This has the L. Okay, we see this when we deal with colligative properties in general chemistry a lot. Molality with the L is given the lowercase m, so not uppercase but lowercase, and it's equal to the moles of the solute divided by the mass of the solvent, not the solution but the solvent, as measured in kilograms. Okay, so very specific in the denominator here, mass of the solvent as measured in kilograms, very, very specific. Okay, this is molality. The beautiful thing, I think, about molality as a concentration unit of measure is that molality is independent of temperature. Okay? If you take a solution in the lab and you warm it up considerably, you heat it up or cool it down, okay, you may change the volume of that solution. You won't change how many moles of solid are present, but you may change the volume. So basically what that means is the molarity of a solution is temperature dependent, because if I'm changing the volume, I'm changing the molarity. On the other hand, with molality, neither one of these terms will change with temperature. So molality is temperature independent. Okay? That's molality. So let's work a very quick example problem as part of this video. And I've worked most of this out so you can see it well. And we just kind of get through it quickly here. Let's say that we're going to prepare some sort of beverage. This looks like it's an alcoholic beverage because we're mixing some food grade ethanol. This is the formula, molecular weight, density of the ethanol, 20 to 80 by volume with water. Okay, so here we're mixing liquids and we're told the mixing ratio by volume. First thing we want to know, what is the volume percent ethanol? Well, that's not hard because we're kind of given information right here about that, okay? We're going to assume that when you mix these 20 to 80 by volume, you equal 100 milliliters, okay? That's part of our assumption. We made that earlier. We're still going to make that here. If that's the case, then I take the volume of my solute divided by the total volume, 20 divided by 100 times 100 to express as a percent. And we can quickly see that it's 20% V/V, or 20% by volume. All right, easy enough, easy stuff. Next question then. What is the mass percent of ethanol in this mixture? Okay, the mass percent. Well, first things first, do we remember what the mass percent equation is? Well, if you don't, I got it written down here at the bottom in words, okay? It's the mass of the solute, here ethanol, divided by the total mass, and we're also going to have to multiply that by 100. Unfortunately, I left that off the slide, but that needs to be multiplied by 100 to express it as a percent. So we need to know the mass of the solution and the mass of the ethanol. So we have a little bit of calculation work to do. We'll assume that we have the same 100 milliliter volume of the solution that we combined in the first part. When we did that, we had 20 mils of the ethanol, and we had 80 mils of the water. Okay? So can we compute the masses of both of these? I think that we can, because we were given the density of ethanol being 0.789 grams per milliliter. So it's just basically a unit conversion. Okay? So if we take our volume of ethanol, which is 20, and we multiply it by our density, the volume units cancel and we're left with grams. So when we do that, we find we have 15.78 grams. That's just 20 times 0.789 if you're following along. That's in grams per milliliter. This one's in milliliters. Units cancel and we just got grams, okay? Similarly, we can figure out how much water we had in grams because we can multiply the density of water times the volume. We know that we had 80 mils of water. We're going to assume the density is 1 gram per milliliter. So we have 80 grams of water. As a consequence of this, we can now figure out the total mass by adding the ethanol mass plus the water mass. Multiply by 100, we have 16.48% by mass ethanol. Now you can see why it's important when you're reporting your results to show which percent you're talking about. If I just said, oh, it's 16.48%, well, is that mass percent? Is that volume percent? If I don't tell you it's mass percent, you might think it's volume percent. And of course, we already said the solution was 20% by volume. Okay, so you got to report, is it V/V, is it M/M? You got to tell people which measure you're computing here. That's very important. Okay. All right, let's move on. What is the molarity of the ethanol in this same mixture? Okay. Well, on the previous page, we said that this was the mass of the ethanol that we used in 100 milliliters of solution. Okay. So all we need to do is take that mass and convert it to moles by dividing by the molar mass of the ethanol. Okay. So that's easy enough done. And you can see I've done that here in this step. I've taken my mass divided by 46.07, which was my molecular weight. It's in grams per mole. The result of this calculation is the moles of ethanol that I'm using, of course. And then all I do is divide by my volume in this last step to get into liters volume. So it's 100 milliliters, which is 0.1 liters, which yields 3.43 moles per liter ethanol. And I'm done. If I want to know the molality of ethanol, I can certainly calculate it. But before I do that, I really need to do what? I need to remember my formula for molality with the L, which is also the little m, the lowercase m, okay? So I like to always keep track of my formulas because it helps me think about, well, what do I need to solve for? Well, if I remember back to my formula, moles of solute was in the numerator, just like it was for the molarity equation. They don't differ there, okay? But where they do differ, and it's important to remember this, is the denominator is not liters of solution, but instead, it's very specifically the kilograms of the solvent, and only the solvent. That's got to be expressed in kilograms. So this is the information that we need. Now, in the previous problem, we decided we could figure out how many moles of ethanol were present by taking the mass divided by the formula weight. Pretty standard stuff here. 0.343 moles of our ethanol. Now, how much solvent do we have? Well, first off, the solvent was water. Okay, that was present in the most quantity, or else determine the phase. We had 80 grams of it. So all I need to do is convert that to kilograms by dividing by 1,000, because there are 1,000 grams in 1 kilogram. The gram units cancel. There are undesirable unit. I convert to kilograms by doing the division, and I find that is my number of kilograms. In the last step, I take my number of moles of my ethanol, divide it by my kilograms of solvent, found that my molality is 4.28. If I wanted to say that in words, I could say it's 4.28 molal. If I wanted to say this in words up here for molarity with the R, I'd say it's 3.43 molar. Okay, that's how we would describe it in words. Alright, so now you have seen several different sample calculations regarding molarity, molality, parts per notation, and mass percent. One of the key things that you can do to help yourself here make it through the semester is understand what these definitions are. That is, their definitions. That's very important. Understand how to use them. Understand when we might use them, whether it's a concentrated solution or not. And then lastly, it's very important to be able to convert between the units, like go from molarity to parts per million, or parts per billion to molarity. Those types of calculations tend to show up a lot on exams. So if I was going to give you some advice here at the end of the video, it would be to definitely make sure you know how to do that. That's also important. All right, thanks. We'll see you next time.